Well, I guess with it being around 100 degrees right now at close to 11 a.m. in the morning, you're probably not that upset that we're not meeting. Although we're not meeting in person, although our room does get nice and cool, so that's nice. It's nice to be in air conditioning. It's interesting how I've been reading how a lot of the Europeans that are here for the World Cup, who are here for the World Cup, are have interesting reactions to our love of air conditioning because many people don't have air conditioning in Europe. I don't know about the other parts of the world. I'm assuming similarly in other parts of the world too. But this articles I've been reading been talking about European fans. So that, but I'm glad we have air conditioning. Although in the room I'm sitting in now, I don't actually have air conditioning. I have a fan and I feel great. You know, you can always get around things if you plan appropriately and set up your rooms well. All right, so today we're going to talk about experimental designs. I when I wrote the book, I divided it into two chapters, and it was because of the pandemic itself made looking at natural experiments very intriguing. So I think when I do the second edition of this book, I'm going to merge them into one. But I think the importance of the natural experiment is phenomenal, given that what we're learning about research right now, and it includes yourselves, that we deal with samples and samples just so random and we never know who we're going to get. Having something like a natural experiment is something we should actually covet and and use whenever we have an opportunity to do take advantage of it because we can learn so much from experience. Most everything in life is a natural experiment. Very rarely do the conditions in life match what you see in a paper. That's one reason I'm not a fan of the term evidence-based research, right? Evidence-based being the adjective here, right, to describe research. I'm not a fan of that because for it actually to exist, the evidence has to be exactly like the treatment, and it never is. You go into therapy, for instance, with a client, you're not going to be doing everything by protocol, following some research paper. You kind of go with the flow of what the client gives you. So I would never use that. I mean, unless I have to, but I wouldn't use it as something as a as an adjective in describing research. So when we look at experiments, we can broadly divide them into two categories: weak and strong experimental designs. And we'll start with these strong experimental designs. So the strong experimental design is the randomized controlled trial, right? See the R is random. So random is really important here, being random assignment. And this isn't the same as random sampling, where we pick people at random from the population. That is very important because, as we know, that allows us to generalize to the population. Here, we're randomizing individuals to different levels of our independent variable. An experiment, our RCT in particular, is the only method that allows the researcher to infer causation. I mean, I, I should say to not just to infer causation, but to claim a causal relation. You can infer causation from whatever you want, right? A correlation, but you're going to have less power in your argument if you use a correlation rather than a RCT. So RCT is extremely important. To infer causation, a study must have what's known as internal validity. So internal validity is established when we can show that the manipulation of the independent variable is the sole cause of change observed in the dependent variable. that contrasts with external validity, which is that the study generalizes outside of the lab setting. The two are inversely related. The reason for that is to establish internal validity, we have to control carefully for all possible competing causes, right? And in doing so, we generally reduce the ability to generalize our findings to the population as a whole. We create a laboratory setting that's very stale, very sterile, I should say, not stale, sterile. I picture a person wearing a white coat in a room with perfectly controlled temperature, pressure, humidity, everything's perfect. And now you can eliminate all these possible light is equal for all participants. Nothing there, maybe blank walls, no paintings or anything on it. Very sterile, but then we can actually make this determination. Aha, it's our manipulation of the independent variable, which is causing change in the dependent variable. Speaking of those terms, the independent variable is the variable we manipulate or the researcher manipulates. They manipulate this to see what its effect is on the dependent variable. Examples are in a drug study would be something like levels of treatment. Say if you're using my famous sunshine pills, you could have high, medium, and low dose sunshine pills, or something like mindfulness versus cognitive behavioral therapy. Then you have a control group, and the control group could be something like a placebo. Well, it would be a placebo if we're dealing with a drug study of some sort, right? Or even with a vaccine, right? So in a drug trial, you'd have, depending on how the drug is administered, you'd have a sugar pill. So it's an inert substance. It does nothing basically. Or you have saline. For instance, if you're injecting, you can inject an individual with saline, right? In non-drug trials, the control is a little bit more difficult to establish because it's difficult because what the placebo does is it controls for expectation. And so when we have something like a sugar pill or saline, and if somebody believes they're getting the substance, so they expect it to work and it's going to have its effect, it's going to have this what they call a placebo effect, right? In a non-drug trial, how can you establish that? The closest, in my view, to a placebo in a non-drug trial would be something like comparing cognitive behavioral therapy to mindfulness. the the closest thing that we have to a placebo is a waitlist control. Because in a waitlist control, you know you're going to get the treatment, right? So maybe there's that expectation that it'll work. So that's it. But other than that, usually you have something like an information pamphlet or maybe a video or a lecture, or it could be treatment as usual. Generally, it's treatment as usual. So if in the example I have with a CBT versus mindfulness, mindfulness is more novel in terms of the way we use it now. I mean, it's old, of course, but in terms of the way we use it, comparing it as a treatment for, say, depression, CBT would be the traditional treatment. So that's what we call treatment as usual. In those cases, we look to see if the treatment is either superior or it's not inferior. And the non-inferiority is actually very important because, and we can think of this not just in non-drug trials, but in drug trials as well, when we're comparing, say, a generic to a name brand, you don't necessarily care that the generic is superior to the name brand. You just care that it's not worse, right? So similarly, if you're comparing, say, a treatment that's a lot cheaper than CBT, non-inferiority is actually a good result. So placebos control for expectation. That's what they do. How important is the placebo effect? Well, for a treatment to work, it must be better than the placebo effect. It definitely has to be better than the placebo effect. Placebo effect is always there. I worked on this one with one group that was creating well, this guy already created it. It was one of these I don't even know how to describe it. It was this device that stimulates your brain. I can't remember what it's called. But this is I've seen this before, and I even saw it in when I was a researcher at UPenn, and there was medical practitioners who actually use this. So there's stimulation of the brain, but at a very low level, and it somehow has an effect. We don't know why, but it does have an effect on behavior. It's good for treatment of depression, etc. Seems like it is, at least. So there was this group that was creating it, and a separate or had a device. This guy was from Russia, I recall, but the company was local here, and the scientist was having a hard time getting it through the FDA. Even like non-drugs, but medical devices have to get FDA approval. And he was having a hard time because a lot of the studies, preliminary studies, were done in Russia, so they weren't, I guess, they weren't trusted. But that was interesting. But I know that when we were doing it, we just had to keep on showing how much more over a placebo effect there was. And that was key because the placebo effect is always there. Well, now I recently I started adding this, and just because you read things, and we generally care more about the placebo effect where you expect positive benefits, but there's also something known as a nocebo effect. I don't know if you knew that or not, but sometimes we expect negative reactions to something, and then we have a negative reaction. So you have like a negative response to a placebo. It's like you believe, oh no, this drug is going to have side effects, even though you're getting the placebo. So you experience the side effects as well. Okay. But there are things that can I don't want to say cause, it can trigger this type of negative response. I don't want to say cause because we don't want to use the word cause. You should avoid using the word cause as much as possible, unless there's an experimentation backing it. And that's in any language, even if you're just speaking in casual speak too. I would just avoid that. But one can experience negative reactions for a lot of factors, including something like price. So, for instance, if you think the generic, I know people who won't buy generic, whether drugs or anything compared to a brand name, because they think that a generic is inferior, even though it has the exact same ingredients. So they'll think, oh no, it doesn't work. Well, see, I'm still sick. Or media misinformation. I remember people saying that the COVID vaccine causes people to become magnetic, and maybe some of you saw this as well. There were these videos where I remember this woman in this hearing sticking a spoon to herself. Of course, she was probably sweating. uh, it was funny. But good communication about the benefits and side effects of the medication treatment can reduce the nocebo effect. And then making sure that the patients understand the information too. So that's key because you don't want people to experience negative effects of something. That's something else as well. There are multiple types of random assignment. The simplest of all is, as you may have guessed, simple random assignment. So basically, each individual has an equal likelihood of assignment to the treatment group. So if you have three groups, there's a third chance to be assigned in each one. Sounds great, but there's no guarantee of equal distribution to the various levels. Now, let me just make sure you understand. Well, in number and also in demographic characteristics. Those are two different things, right? Number and having actual, if I have 30 people and I have three groups, getting 10 in each group, right? I might not get 10 in each group. Now, there's a caveat here because if I have all 30 people in advance, I might just count one, two, three. First one goes in group one, second. There's no way I'm not going to get an equal number of individuals in the different levels. So that's why I added the caveat here is recruiting occurs over time. Because in many studies, we recruit over time. We don't have all the participants at first because people don't want to wait. Neither do the researchers. And we recruit people, we give them the treatment, and then move forward, right? So there's so if you just do a simple random assignment, you might get more people. I mean, because you can go on these what are these roles, right? I forget what they call it in gambling. Heater, like a heater. Everybody goes into group one, right? That's plausible in terms of probability. There's no guarantee that you're going to get one third, one third, one third. And of course, in demographic characteristics, we'll talk about that in a second as well. To deal with the number of participants per group to make sure we get an equal number of participants to the various levels. So I say levels of the independent variable, right? Levels. So high, moderate, low dose versus placebo of sunshine pills or something like that. We can use something known as block randomization. This is kind of fun stuff. It's not as mathy, but it is some math here. Important is that you understand that there's this option here. Okay. Listen, if you're doing a study 5 years from now and you're like, oh God, I can't remember. I know Dr. Rodriguez said something about block randomization. Sounds like it will work, but I don't know how to do it. I mean, you can just look it up again. I mean, that's the way most researchers work. Sorry, I'm drinking gum. Forgot what this is. Gatorade something. I was cycling this morning. It was really hot and humid. But I got my work in before it got too hot. So this is how it works. It's nice steps here. So you define blocks of participants. Make sure that they're not too large. So you're going to have these blocks in which you're going to have 4, 6, or 8 participants. Again, you're going to have maybe 100 people in your trial, but you're going to make these blocks that make sense, right? And a block must be a multiple of the number of treatment levels. So with 2 treatment levels, say treatment versus placebo, your block size can be 4 or 6, right? I mean, again, you don't want to go too large, right? And you'll see why in a moment. If we have a block size of 4 and we have 2 levels to our treatment, we can actually calculate how many blocks we need. So if we do that, we get 6 possible blocks. So let me just show you how this is done, okay? Again, this isn't, you're not going to have to do this on an exam, but you should understand how this is done. The process that we go through to get the number of blocks we need. So we think about it this way: how many ways can we arrange blocks of 4? Well, how many different blocks of 4, possible blocks of 4, are there if we have 2 groups? So we're arranging blocks of 4 participants into two groups: control versus treatment, right? That's what our interest is. And we can use something known as the binomial coefficient. I may have shown this to you when we went over our stats stuff, when we were talking about determining if we're going to have a higher family-wise error rate in an experiment in an ANOVA. I may have done that. I think I did. But really, you can do something called 4 choose 2. This is known as a binomial coefficient, or choose function if you prefer. So we have 4 blocks of size 4, and we're arranging individuals into treatment versus placebo using this equation. Again, you don't need to know how to calculate it, but if you're interested, this is a 4 factorial. So it's 4 times 3 times 2 times 1 times 0 factorial. 0 factorial is 1, right? Can't if you multiply everything by 0, it would be 0 divided by 2 factorial times 4 minus 2, right? That's kind of, there's an equation for this if you want to look at it. So there's 6 possible blocks here, 6 possible blocks if we work this out, okay? So let's say we have 8 participants and 6 possible blocks of 4 assignments. So we can assign the first 4 participants to any one of the 6 possible arrangements. So this is how we're arranging the first 4, right? So if I have 8 people, I could just use these first 2, right? Treatment, first person gets treatment, second person gets treatment, third person gets control, fourth person gets control. That takes care of 4 people, 4 of the 8, right? Or I can use this one here. The 5th person gets treatment, 6th gets control, 7th gets control, 8th gets treatment, right? I can use any of these. So I can select those at random, right? If I have more than 8 individuals, I mean, sorry, if I have this is 8 times 6, right? If I have more individuals than I have I have 8 times 6, 6 times 4, sorry, 24, right? If I have more than 24 individuals, they have 30 individuals, and I can just start recycling blocks, right? Just recycle the blocks, start again. That's it. So, I mean, I'm going to make sure that I have, because each of these blocks has an equal number of treatments and an equal number of controls, right? So you're going to get equal size groups. So one of the weaknesses with this is that somebody knows to which block individuals were assigned. So it's easy for a researcher to figure out assignment. And that's something we have to prevent because we don't want the researchers to know to which groups the participants were assigned. We call that blinding, right? So where like you have a blinded study, you have single versus double blind versus triple blind. In a single blind study, the participant doesn't know to which group they're assigned. That's at minimum. You need that, right? You don't want the participant to know if they're in the treatment and control, because if you know you're in the control, what's the point? The effective expectation will disappear. Double blind, both the researcher and the participant knows to which group they're assigned. I mean, does not know to which group they're assigned. So that's better, right? So as researchers, we may have agendas and we can like as one of my colleagues used to say, stirred the chi. I don't know where she got that from. It was funny. You know, cheat basically. Or there's a triple blind study where neither the researcher nor the participant nor the statistician or data analyst knows. So that's even better. So somebody's got to know. There's probably some research manager who would know, right? Stratified assignment. So this is more to deal with variables that are important, especially key demographic variables that, so I had mentioned that in randomization, one of the problems is that you can have the unequal number of individuals or participants. They don't have to be human, it could be animal, non-human animal, assigned to different groupings, but you can also have people with, you can have a slew of individuals with a specific demographic in one group and other groups being different in their proportions, right, of that demographic. And that's not a good thing either, because then demographics becomes a confounding variable, right? And we don't want to have any confounding variable because in order to show that we have internal validity, we have to show that it is the independent variable that causes change in the dependent variable and nothing else, right? So if there are confounding variables, that's not good. So, right, confounding variable is a variable that it competes, right, with the for causation with the independent variable. Technically, a confounding variable is a variable that's related to both the predictor and the outcome, right? It's related to both of them, but it's a competing cause. In most research, people ignore them and they don't really include them in their analysis. You can, and I probably will talk about that a little later today, or maybe in a different class. Right? So what we can do to ensure a better allocation across groups is to stratify. So we stratify on a characteristic of interest, right? So for instance, we could stratify by gender first. So we got males and females, and then randomly assign within each gender, right? Randomly assign females to either control or experimental group, males to the control or experimental group. We can add to that block assignment and make sure we have equal um, number of individuals in the different groups. So we can put things together, right? That's awesome, huh? Okay. Now let's talk a little bit about some other methods that we can use, but I'm going to focus primarily on, again, if you have all the participants at the start, it's really easy to, if you have all the participants at the start, it's really easy to deal with randomization. Again, you can use like 1, 2, just numbers, right? You might have to deal with stratification though, because you can't guarantee that you're going to have people of different, whatever your demographic is. So you can mix in stratified assignment, right? Stratification, but it's different when we're recruiting people in a sequential fashion. Because it's not always possible, as you will learn if you ever have to do a study, especially in counseling. to have all participants in advance. It's a lot of work. I mean, it's possible, but you'd have to have a lot of money and a good, strong team of individuals. But in general, people come in when they can because of their complex schedules. So certain treatments require participants to come in one at a time. A good example is one of the researchers I work with. She does this buffet challenge for eating disorders where I guess somebody's who has a disease like anorexia nervosa or bulimia come in and they get this buffet and they just see what they eat and I guess they do weighing and stuff like that of the food or and looking at all the nutrients that they eat and then we'll see how they respond to that. That's not something you can just bring a whole bunch of people in at one time. It would really introduce too many confounding variables. Like if I had two people come in together, they could talk to each other and that could just destroy the the quality of the study, right? Relationship counseling. I mean, you can't do that with. I mean, you could do groups, but then that would be a different type of study. So where in these cases we acquire people sequentially. So this is mostly what you'll see in research because you're getting people one at a time. A really cool way to deal with this is something known as adaptive randomization. So you have software that recalculates. So again, in simple random sampling, it's really easy to calculate the probability of assignment to different groups. But we just do it and assume that that probability remains constant. Well, it does remain constant, but we ignore the probability unless you're doing stratification. But even then, when you actually do the simple random sampling, you're assuming that the probability is the same for everybody, right? And it is, but that doesn't guarantee that you're going to get what you need in terms of the distribution. So one way to deal with this, especially again in these when you're doing sequential recruiting, is to use adaptive randomization. So software will assign a probability, excuse me, it'll recalculates the assignment probability after the allocation of each participant to the treatment levels. Why is that important? So think about it. So if you have two groups and then everybody has a 50-50 chance of getting into treatment versus placebo, if I get one male, well, it would be best if the next male would go to the control group. First one goes in treatment, second goes to control, right? And what if I get two that go into the treatment group and zero into control? I don't want the third one to go into the treatment group. So I just change the probability of them being assigned to the control group into the treatment group. So that's going to actually allow for more of a balanced assignment. I think that's so cool. I love all these innovations. I've used that one before as a so a lot of times I have to help people design these like when they're writing grants, because when you write a grant to get money to conduct a study, everything has to be laid out really well in advance so that we know what's going to happen, right? There's two types of randomized control trials. Again, we're talking about the stronger type, but among them, there's a weaker and a stronger itself too. There's always diversity everywhere. There's the post-test only design, still randomized because you have random assignment to the different levels of the independent variable, and you assess the effect of the treatment on the dependent variable. The strength is that you have a control group and that you have two strengths, right? And you have random assignment. Weaknesses are there's no pretest, so we can't compare what happens after treatment to pre-treatment, right? But if everybody was already low on depression or something like that, and you're doing this study to improve happiness or something like that. And the other one is you cannot test for equivalency on the covariates before the introduction of the independent variable. That's actually very important to do in a study. Like when you say, well, we had randomly assigned individuals to these two groups, you should test them on the covariates. Covariates are another way to call to this to define or to label a confounding variable, called a covariate. Usually confounding variables and covariates are not manipulated in any way, or they're not assessed. And I say usually because you can, right? Right. The pre-test, post-test design is the stronger of the two. So you have random assignment to different levels of the independent variable. You assess the effect of treatment on the dependent variable. Okay. The strengths are you have a control group. So you can test for equivalency on the covariate and dependent variable because you have a pretest, right? So now you can do that. And you can look at the assessment of a time by treatment interaction, a time by treatment interaction. So treatment is different levels of your independent variable, and of course the now you have this effect of time because you have a pre to post, so time comes to play in there, right? You can have pre, post, follow-up. You can have three, whatever, but you have time is coming into play, and you'd like to see if there's an interaction between treatment and time. So we're testing for moderation, right? So another moderation means that this some thing changes the effect of a variable on the dependent variable. In this case, we'd say, okay, our independent variable, we'd call that a moderator, an effect moderator. And then time always has an effect on everything. Like if I'm looking at depression, I'm going to have an effect of time on depression. Not everybody stays constant at the same level. So time is one variable, right? It's one variable, one independent variable. And the other is your primary independent variable, right? You have your primary independent variable is your level of your treatments. So if the effect of time on your dependent variable, so let's say the effect of time on depression differs for individuals who are in the treatment group versus the control group, then this independent variable, our treatment, moderates the effect of time on our dependent variable. And that's really cool. So you can do that. Right? That's what an interaction does. This is the best possible research design. So when people talk about an RCT, this is what they're talking about. Randomized control trial. You have pre-test, post-test, and you have random assignment to the different levels of the independent variable. This little table that I created shows different types of weak experimental designs. And some of them get closer to being strong, right? Especially the ones that under non-equivalent designs are closer. But there's weak strengths and weaknesses to all of them. First is a one-shot case study design. Then you have one group, pre-test, post-test. Then you have an interrupted time series design. I'll show you all of these in a second. Then under the non-equivalent, we have post-test only. So these two are the same as I discussed under the strong experimental designs, except for they're weak. Okay. So with the one-shot case studies, we look at participants after the event only. So there's a lot of problems with this one. So first of all, we cannot control for pre-test levels in the dependent variable, right? So we have no idea what they were before. So no control group. So we have a possibility of a placebo effect and no way to account for other potential confounding variables. So this just, it's like, okay, well, I did this, and hey, how did it affect you? That's basically all I'm saying. I give you a Diet Coke. Do you like it? Oh, I love it. You're not comparing it to anything, right? Is it better than Pepsi? No, no, nothing like that. Diet Pepsi. A one group pre-test, post-test design. So now you have a baseline. A baseline is the first measurement. We call baseline the first measurement, and we can compare movement on the dependent variable. Movement means change in the dependent variable to that baseline, right? So we can look at what's the effect of the intervention right? By looking at whether there's change from baseline. So usually you'll have a baseline. So like say I collect measures on happiness, I introduce my treatment, then I measure happiness again, right? That's better, right? But we have no control groups. Mhm. One of the issues that control without any, well, so obviously we don't have any random assignment if there's no control group, right? One of the really, I might ask you this on an exam. What's the key difference between a weak and a strong experimental design? The main difference is random assignment. There's no random assignment, right? If no control group, there's no random assignment, right? Everybody's going to the experimental group. One thing that's important to look at in all types of repeated measures designs, whether it's strong or weak experimental design, is the spacing between measurements, because that can affect recall. So like for instance, if I'm asking you for your opinion about something, I do it today and then I do tomorrow and then the next day, you're probably going to remember what you said yesterday and try to be consistent, right? So we have to be careful with that. Another way to look at that is if you've ever gone wine tasting, when people go wine tasting, they have to wash out their palate in between tasting the different wines. But if I tasted a wine on Monday and then another one on Tuesday, my palate will be pretty clean, right? So understanding how spacing can affect that basically introduces another confounding variable, right? It introduces another confounding variable. And again, you want to eliminate as many confounding variables as possible. So always think about that whenever you're doing any kind of design, what's the impact of time in the measurement process? The interrupted time series design, what this is done, why we do this one is to control for maturation. So this is particularly important when we're dealing with like children and adolescents because they change so much. I mean, if you're looking at some treatment to see how it affects weight, and people will weigh more anyway over time and as they get bigger. So what you want to do is collect data prior. So here's an example where 6 measures were acquired prior to the intervention being introduced. Then you introduce the intervention, and then you collect data afterwards. And what you're hoping to see is something like this. See this black line right here? So there is change, right? There is change over time, but we don't know if that change is due to the treatment or if it's due to time itself, right? So or maturation, to eliminate that, we want to see a displacement. So the slope remains the same. Slope, the gradient, the how steep it is, remains the same. So there's still change, but we'd like to see. It's like here. This is an example. We're looking at time on cognitive ability. So cognitive ability is increasing anyway, but you get a much bigger leap, right, when you introduce the treatment here. Right. So this is an interesting design. I equate this a lot to the single participant research design. Because in the single participant research design, I know you were answering questions on that online. When we deal with a single participant, you collect data to establish a baseline, whatever the baseline is. And it may not look like this, right? It could be flat, right? Like say if I wanted to test a new treatment on getting people to adapt better to difficult information, yeah, I'd like to establish a baseline. I might collect heart rate data or something like that, interbeat interval, interval between beats, and see what it's like prior to the intervention. And I establish a baseline, introduce the intervention, and see what the effect is. If my treatment works and people get calmer, the interbeat interval will be longer. I like this. I like using that as an example because in my Fitbit app gives me data on interbeat interval, which is really cool. I had a faculty member when I was a doctoral student, Stephen Porges, who's really famous for studying cardiac vagal tone. So that kind of got me interested in this. So vagal tone is basically what I'm talking about, interbeat intervals. But say I introduce my treatment and the interbeat interval gets a little larger, so it's more person's more relaxed. That's what you want them to be. They're not as worried or whatever. So then you introduce that. So you want to see that change, right? This is, I'm talking about a single participant design. And this is just, it's an offshoot of what I'm discussing here, just to be clear. Then what you could do is you could take away the treatment if you want to establish that the treatment works and see what happens. Let's say you take away the treatment and then the person's interbeat interval returns to where it was prior, or it's lower than it was after you introduce the treatment. That's how we can take this, what I'm showing you here, and translate it into a single subject design. I think it's really cool. Again, here we have no control group, but one of the beauties of any repeated measures design is that the individual serves as her own control. That's pretty cool, right? Because while certain things can change, fundamentals will not change, like who your parents were. That's not going to change. Your genetic code, I mean, you can have epigenetics. I don't know if you're familiar with that, where there's can be a turning off and on genes and stuff like that. But that's not what I'm talking about. I'm talking about the genetic code itself. It won't change. So certain things won't change in an individual. So you're already controlling for that. So these repeated measures designs within subjects designs, whatever you want to call them, panels. So sometimes people call them panel studies, time series. They have a really nice benefit of people serving as their own controls. Then now we have the non-equivalent group designs. I think these are the strongest of the weak experimental designs. So we have the non-equivalent post-test only design, very similar to what we talked about with the strong experimental design, except for we have no random assignment. So that's a weakness. So the groups are non-equivalent. That's why they're non-equivalent. There's no random assignment. And then there's no pre-test to assess change. And of course, you can't check what the effect of the if people differ on covariates, right? Control variables. Then you have the non-equivalent pre-test, post-test design. So now you do include a baseline. You do have a control group. Again, they're non-equivalent because of no random assignment. Last thing I'll mention, and this is just goes with all experimental designs and all studies in general, is a major weakness is selection bias. So you should always keep that in mind. People who participate in studies are different from people who don't participate in studies. That's something that needs to be discussed. It's interesting though, I do a lot of work now with simulated data, so I don't have to worry about that. Actually, we should be doing this everywhere. We can get rid of animal research, non-human animal research, right? By just doing simulation of everything. Should actually teach a class on that. Maybe so I'm going to teach a stats class to the doctoral program. I think I might add that in there using simulated data. Because the study I'm about to submit manuscript is based on simulated data. It's really easy to do and you get really cool results without having to deal with people and then worry about random assignment because everything's simulated. Yeah, but then you miss out on some things too. So that's for another time. Matching. When we can't randomly assign, sometimes it's just not possible for ethical reasons. I can't randomly assign individuals to cigarette smoking exposure versus non-cigarette smoking exposure. So it's really hard for me to use random assignments. So what can I do instead? Well, I can match people. So literally when I match people, I'm treating them like they're exactly the same person, like in a repeated measures design. But I match them on certain variables. It's like just to make this as clear as possible, like match two females, right? If I want to match and eliminate the or control for the effect of gender, match females, match males, right? In the experimental versus control group. So this is a pair, that's another pair, etc. Can match people on things like income range, education level. You have a high school diploma or less in the experimental group. You have a high school diploma or less in the control group. So I match people on those, right? I can match people in a case by case fashion, right? participant number one is matched with participant number three, right? Right. This improves the internal validity of the study. It's not enough to to compensate for not having random assignment, but it's pretty good. It also reduces variability because now we're matching people on these variables. It also eliminates that variable from possible analysis, which is a drawback, right? Maybe I want to include gender as another independent variable. So that's a drawback. Another thing I can use is something known as propensity matching. This is cool. So I already have my data, boom, and I create a new dependent variable, a dichotomous, two levels, right? It's a binary variable. This is actually a control variable. I'm sorry. So I got thrown off by somebody calling me spam. It says potential spam, so I'm not answering it. What if it was a survey, right? I was talking to you about surveys and people don't answer phone calls, right? Hi, I need a survey for I don't know, whatever. That's why it's so hard because I see that potential spam now. I'm like, forget it. All right, so I want to match people, but one of the problems with matching people case by case on different confounding variables is it gets more and more difficult to do so. Like, so I want to match people on gender. Okay, well, let's so we eliminate the effect of gender. Let's also match them on income range. Okay, all right. So people who make between 25 and $30,000 a year. Well, let's also match them on something else, educational. So as you do that, it becomes more and more difficult to find participants that fit in all those categories. So it's just really hard to do. So a better alternative is something known as propensity matching. Those mathematicians are always doing some new stuff, and I love it. So you create a discrete variable. The discrete means a binary in this case. Well, actually, no, it doesn't mean binary, but it's a discrete variable that can be binary in this case, but depending on how many treatment groups there are. So you could have, if you have two, it's a binary, right? So you have treatment versus control, but you could have different levels of treatment, right? Because you're randomly assigning individuals to different levels of the independent variable. So in this case, we create a discrete variable. And this is going to be actually a dependent variable in a different analysis. So we're going to calculate the probability of treatment group assignment. And notice that I said after assignment, so we already assigned individual. So now we want to know what's the probability of treatment group assignment conditioned on these covariates like gender, et cetera. And then we match participants in treatment and control by the propensity score. Okay. So score should be the same or quite similar for individuals that are matched in the two different groups. Okay, so this is not matching by a specific variable. It's matching in all the confounding variables. That's pretty cool. See, those mathematicians, statisticians are awesome. See, they create stuff that makes the world better. We should have a International Statistics Appreciation Day for people who like doing this kind of stuff. Yeah, I'll lead the charge. I'll lead the charge. All right, so what statistical methods are useful for experimental designs? Oh, there's so many. So let's just talk about a few of them. Mixed ANOVA, so that's an analysis of variance, right? So now this type of analysis of variance, you have a mixture of within and between effects. So within effect would be the repeated measure. So for instance, I could have baseline treatment, we say end of treatment. That's when the EOT end of treatment and then follow up. So like here's an example, pain surgery, pain before surgery, pain after surgery, and at 6 month follow-up. So the question is there an overall change across time? So that's one of the outcomes you'll get is there an overall change across time? Then you have the between effect. So you have between, you have the independent variable, this other independent variable, and it's So I like to separate them, even though time is itself an independent variable, right? But I'm going to I separate them. I say when I say independent variable here, I notice that I saw this discrepancy. I told you I like to catch things that I wasn't thinking of when I wrote certain things, but they're basically both independent variables. But when we think about the independent variable, we're generally thinking about the treatment. So maybe I should reconceptualize that or rewrite it when next time. So something for the second edition of this book. Well, you have the treatment variable in the control group, and you basically want to see is there a difference overall based on those levels across time? So you aggregate everything. Is there a difference in the different levels? Then you do a within by between interaction. We introduce them to each other. Hey, for you. So an interaction where we talked about moderation effects, that's just a product term. You just multiply two things together. Okay. And if significant, you interpret the results. That's actually a lot of fun to do, and it's complicated depending on the nature of the variables, right? If you're dealing with continuous variables versus I mean, continuous versus discrete variables, the interactions can be really complicated. What if I have more independent variables? See, some of the weaknesses here, one of them includes limited number of independent variables because I can have my treatment as an independent variable, but I can also have gender as an independent variable, right? So let's say we have male, female, non-binary, three, right? And then I'll do a treatment by gender interactions. I create all these different levels, right? It gets complicated. And then what if I add another term and another independent variable? Like let's say, okay, let's include socioeconomic status as measured by education. So now I multiply those three together. Can get really, really complicated and messy and extremely difficult to interpret. But it also requires a continuous dependent variable. And when I talk about continuous, I mean the dependent variable itself is continuous. So it's something like weight, height, etc. Assumes multivariate normality. So I showed you that normal distribution, that really beautiful bell curve, but that focuses on one variable. If I have two variables, think about those two overlapping, right? One cutting the other in half. You get this really pretty looking, almost like a Liberty Bell, but now not just two-dimensional. And then as we go add more in dependent variables, the dimensionality increases. So repeated measures are dependent variables. If I have three repeated measures, we're already in three dimensions, right? If I have 10, then, tough luck for us, right? I said one dimension, two dimension, three. So I'm a two, not one dimension before. Yes, difficult to include time. Oh, you can't include time varying covariates. That's an interesting one because covariate again is a confounding variable, but sometimes the confounding variables aren't constant. Like we use gender as a confounding variable, assuming that people don't change their gender, but people do change their gender identity. But in general, that tends to be a constant that you can measure at baseline. But what if we're dealing with something like, I don't know, we're looking at depression and we're dealing with anxiety. Anxiety and depression covary a lot. So it would be better instead of measuring anxiety at baseline to continue to measure anxiety and see what the relation is between the two. That's something called as a time varying covariate. And this is something that is hard to do here and really, really difficult to do. I used to say not possible, but I've studied it more. It's possible, but why would you do that? I mean, it's kind of like there's so many better methods. One of them is generalized estimating equations, GEE, right? So you assess change in a variable over time. This is a great, great method. Variable can be anything. The dependent variable can be continuous, discrete. You can assess the effect of time varying covariance and time invariant covariance. Invariant means they don't change, right? So it's got a lot of advantages. Here are some weaknesses. It assumes that the missing data are missing at random. I don't really talk a lot about, I think I talk about it a little bit in this book, but in different, maybe here I did, but missing data is a huge issue, and there's a whole science of missing data. For a method to assume that data are missing at random, what that means is that, okay, I have my full data set, and then I have the data set that I was able to get. And it assumes that this data set that I was able to acquire is a random sample of the full data set, right? That's not usually going to happen because there are factors that can increase the likelihood that data are missing, right? And the worst case is when data are not missing at random. So there's like if you're studying something like depression and depressed people refuse to participate in the study, right? So that those are problems. So this method assumes it. Now there's ways of dealing with that within the method too, but again, there's always a better method that you don't have to worry about that at all. And another weakness is that you actually have to restructure your data. We go from a wide format to a long format. So generally, when you look at data in a spreadsheet, each row will be an individual, and each column will be some variable, right? Like, so if I'm measuring depression 5 times, I'll have one column for depression at time one, one for time two, et cetera, right? But that's called a wide format. But GE wants it to be in a long format. So I'd have participant one, and then under participant one up, each row will represent each of the time points, depression at each time point. It's just it's a minor inconvenience if you know what you're doing. You just what we call that change of transposing the data, the matrix, because that's everything's always in a matrix, right? The data are always in a matrix, but it's not that horrible to do, but it's another little thing you got to think about. So it's just why deal with it? Other possible methods. I'll talk about growth modeling later. I think it's coming up soon. And then the thing that I'm working on myself is area under the curve as an interesting option. So the just real quick on this, couple other notes before I shut off for the day. I'm using the study I'm working on now that I'm done. I just have to restructure it for the journal. You know, I told you that that's the worst part is when you have to structure things to fit the constraints of the journal. But that's one where I was looking at large number of repeated measures, which is what you get. Like, say if I'm doing my Fitbit, I'm getting data moment by moment. So it's not like I have 3 time points. I have like hundreds and thousands of time points. I did a simulation where I looked at cycling outcomes using the Strava app. If you're not familiar, Strava is an app that allows cyclists, runners, hikers, skiers, whatever, maybe swimmers too. I have no idea. I haven't used that, but to track their data, right? Like for I use it for cycling, so I get things like my speed, the hills that I climb. If you have the right tools, you can get cadence, revolutions per minute, power output. Power is measured in watts. It's how much force is transmitted from the cyclist to the bicycle. So you got all these really cool data, and but using some of these methods like GEE would be really, really complicated. So instead, I just calculate area under the curve. When you looked at the normal distribution, it's a curve, and the area under that represents the probability. So why not just do that? So I end up translating, like I did it here. I created 30 repetitions for a cyclist, for 21 different cyclists. I used real data, and then got, I used the data that had from Strava that had times for these individuals, and then I also introduced the standard deviation, which I had to come up with myself because these were all cross-sectional; they weren't longitudinal, so I had to come up with a standard deviation, which is itself something that you have to work on. And then I threw it into this computer program, and it spat out 30 hypothetical rides for these individuals. And then I did it again for 100. And then I calculated the area under the curve using three different equations. Three different equations for each individual, right? One way of calculating it is more traditional way of calculating area under the curve using these like polynomials. You'll see it I have 3 papers already on this. If you're interested, you can look at them. And then the other one is uh, uh, using an integral, a definite integral, so it's calculus, right? They all performed really well. It's amazing. But the point of it is that we can aggregate large amounts of data into one variable, right? So with 100, I had three things I was looking at. I was looking at power, right? In watts. I was looking at miles per hour, and I was looking at time. So there's three things. So the idea was that watts or power would be associated with a decrease in time, right? Controlling for miles per hour. So I just wanted to test using this. I mean, it's not a very interesting study in itself. Of course, the more power you put in, probably you're going to reduce your time. So, but I did this on purpose because I just wanted to see how area under the curve worked under these conditions, and it worked really well, which is great because I reduced. So if you have 100 variables, right, repeated measure, each is a variable, right? So every repeated measures is its own variable. So I have 100 on watts or power, 100 on time, and 100 on speed. That's 300 variables. And I converted it into three variables. So see, there's a lot of different things that you can do when you're working with these kind of analysis. So what we could do it here too, and I could say, okay, well, I could just do the area under the curve for the individuals in the experimental group versus the control group. Just that's just another way of doing it. And then the other piece of news is that the article I'd mentioned that I worked with this high school student got, and it's now she's finished her first year of college. It got published. To me, that's the greatest accomplishment I've had as a researcher. It may be hard for people to understand that when they say, well, what about your dissertation? What about your first major publication? What about your first grant? Nah, this was more impressive in my opinion, given how difficult it is to get published in general, and then to be somebody who doesn't have the credentials yet. This student is what is phenomenal, not just because she's bright, but because she has the drive. People have either one or the other, but put them together, wow. So I'm very proud of that achievement on her part, and I'm so happy that I could be part of it. So that was cool. All right, but so as soon as we get more, we get the proofs and stuff like that, I can start sharing. But anyway, thank you guys. Have a great day.